The following is a conversation with Jensen Huang, CEO of NVIDIA, one of the most important and influential companies in the history of human civilization. NVIDIA is the engine powering the AI revolution, and a lot of its success can be directly attributed to Jensen's sheer force of will and his many brilliant bets and decisions as a leader, engineer, and innovator. This is the Lex Fridman Podcast, and now, dear friends, here's Jensen Huang. You've propelled NVIDIA into a new era in AI, moving beyond its focus on chip scale design to now rack scale design. And I think it's fair to say that winning for NVIDIA for a long time used to be about building the best GPU possible. And you still do, but now you've expanded that to extreme co-design of GPU, CPU, memory, networking, storage, power, cooling, software, the rack itself, the pod that you've announced, and even the data center. So let's talk about extreme co-design. What is the hardest part of co-designing a system with that many complex components and design variables?
Yeah, thanks for that question. So first of all, the reason why extreme co-design is necessary is because the problem no longer fits inside one computer to be accelerated by one GPU. The problem that you're trying to solve is you would like to go faster than the number of computers that you add. So you added 10,000 computers, but you would like it to go 1,000,000 times faster. Then all of a sudden, you have to take the algorithm, you have to break up the algorithm, you have to refactor it, you have to shard the pipeline, you have to shard the data, you have to shard the model. Now, all of a sudden, when you distribute the problem this way, not just scaling up the problem, but you're distributing the problem, then everything gets in the way. This is the Amdahl's law problem, where the amount of speed up you have for something depends on how much of the total workload it is. And so if computation represents 50% of the problem, and I sped up computation infinitely, like 1,000,000 times, I only sped up the total workload by a factor of 2. Now, all of a sudden, not only do you have to distribute the computation, you have to, shard the pipeline somehow, you also have to solve the networking problem because you've got all of these computers are all connected together. And so distributed computing at the scale that we do, the CPU is a problem, the GPU is a problem, the networking is a problem, the switching is a problem, and distributing the workload across all these computers are a problem. It's just a massively complex computer science problem. And so we just got to bring every technology to bear. Otherwise, we scale up linearly or we scale up based on the capabilities of Moore's law, which has largely slowed because Dennard scaling has slowed.
I'm sure there's trade-offs there. Plus, you have a complete disparate disciplines here. I'm sure you have specialists in each one of these, high bandwidth memory, the networking, the NVLink, the NICs, the optics and the copper that you're doing, the power delivery, the cooling, all of that. I mean, there's like world experts in each of those. How do you get them in a room together to figure out?
That's why my staff is so large.
What's the Can you take me through the process of the specialists and the generalists? Like, how do you put together the rack when you know the set of things you have to shove into a rack together?
Yeah.
Like, what does that process look like of designing it all together?
There's the first question, which is, what is extreme co-design? You were optimizing across the entire stack of software, from architectures to chips to systems, the system software to the algorithms to the applications. That's one layer. The second thing that you and I just talked about goes beyond CPUs and GPUs and networking chips and scale-up switches and scale-out switches. And then, of course, you got to include power and cooling and all of that because, these computers are extremely, extremely power hungry. They do a lot of work and they're very energy efficient, but they, in aggregate, still consume a lot of power. And so that's one. The first question is, what is it? The second question is, why is it? And we just spoke about the reason, you want to distribute the workload so that you can exceed the benefit of just increasing the number of computers. And then the third question is, how is it? How do you do it?
Mm-hmm.
And that's kind of the miracle of this company. When you're designing a computer, you have to have operating system of computers. when you're designing a company, you should first think about what is it that you want the company to produce. I see a lot of companies' organization charts, and they all look the same. Hamburger organization charts, software organization charts, and car company organization charts, they all look the same. And it doesn't make any sense to me. The goal of a company is to be the machinery, the mechanism, the system that produces the output. And that output is the product that we like to create. It is also designed, the architecture of the company should reflect the environment by which it exists. It almost directly says what you should do with the organization. My direct staff is 60 people. I don't have one-on-ones with them because it's impossible. You can't have 60 people on your staff if you're, going to get work done. And
so you still have 60 reports. You still have
more,
across.
yeah,
More.
yeah.
And most stars at least have a foot in engineering.
Almost all of them. There's experts in memory. There's experts in CPUs. There's experts in optical.
That's incredible.
Yeah, GPUs and architecture, algorithms, design.
So you constantly have an eye on the entire stack, and you're having to do like intense discussions about the design of the entire stack.
And no conversation is ever one person. That's why I don't do one-on-ones. We present a problem, and all of us attack it. Because we're doing extreme code design. And literally the company is doing extreme code design all the time.
So even if you're talking about a particular component, like cooling, networking, everybody's listening in.
Yeah.
And they can contribute. Well, this doesn't work for the power distribution. This doesn't
exactly.
This doesn't work for the memory. This doesn't work for this.
Exactly. And whoever wants to tune out. You know what I'm saying?
Yeah.
And the reason for that is because the people who are on the staff, they know when to pay attention. They're supposed, if something they could have contributed to, they didn't contribute to, I'm going to call them out, and so, hey, come on, let's get in here.
So as you mentioned, NVIDIA is this company that's adapting to the environment.
Mm-hmm.
So at which point can you say, did the environment change and began adapting sort of secretly in the early days from GPU for gaming, maybe the early deep learning revolution, to we're now going to start thinking of it as an AI factory? Mm-hmm. What does NVIDIA do? It produces AI. Let's build a factory that makes AI.
I could reason through it just systematically. We started out as an accelerator company. But the problem with accelerators is that the application domain is too narrow. It has the benefit of being incredibly optimized for the job. Any specialist has that benefit. The problem with intense specialization is that, of course, your market reach is narrower. But that's even fine. The problem is the market size also dictates your R&D capacity. And your R&D capacity ultimately dictates the influence and impact that you can possibly have in computing. And so when we first started out as an accelerator, very specific accelerator, we always knew that was going to be our first step. We had to find a way to become accelerated computing. But the problem is when you become a computing company, it's too general purpose and it takes away from your specialization. I connected two words that are actually have fundamental tension. The better computing company we become, the worse we became as a specialist. The more of a specialist, the less capacity we have to do overall computing. And so and I connected those two words together on purpose, that the company has to find that really narrow path, step by step by step, to expand our aperture of computing, but not give up on the most important specialization that we had. Okay, so the first step that we took beyond acceleration was we invented the programmable pixel shader. So that was the first step towards programmability. It was our first journey towards moving into the world of computing. The second thing that we did was we put FP32 into our shaders. That FP32 step, IEEE compatible FP32, was a huge step in the direction of computing. It was the reason why all of the people who were working on stream processors and other types of data flow processors discovered us, and they say, hey, all of a sudden, we might be able to use this GPU that's incredibly computationally intensive, and it's now compliant with IEEE. Mm-hmm. I can take my software that I was writing previously on CPUs, and I can see about using the GPU for that. And which led us to put C on top of FP32, we call CG. That CG path took us to eventually CUDA. CUDA, step by step, putting CUDA on GeForce, that was a strategic decision that was very, very hard to do because it cost the company enormous amounts of our profits, and we couldn't afford it at the time. But we did it anyways because we wanted to be a computing company. A computing company has a computing architecture. A computing architecture has to be compatible across all of the chips that we build.
Can you take me through that decision? So putting CUDA on GeForce could not afford to do. Can you explain that decision? Why boldly choose to do that anyway?
Yeah.
Can you explain that decision?
Excellent. That was the first. I would say that was the first strategic decision that is as close to an existential threat.
For people who don't know, it turned out to be, spoiler alert, one of the most incredibly brilliant decisions ever made by a company. So CUDA turned out to be an incredible foundation for computation in this AI infrastructure world. So just setting the context, it turned out to be a good decision.
Yeah, it turned out to have been a good decision. I think here's the way it went. So we invented this thing called CUDA, and it expanded the aperture of applications that we can accelerate with our accelerator. The question is, how do we attract developers to CUDA? Because a computing platform is all about developers. And developers don't come to a computing platform just because, it could perform something interesting. They come to a computing platform because the install base is large. Because a developer, like anybody else, wants to develop software that reaches a lot of people. So the install base is, in fact, the single most important part of an architecture. The architecture could attract enormous amounts of criticism. For example, no architecture has ever attracted more criticism than the x86. As a less than elegant architecture, but yet it is the defining architecture of today. It gives you an example that, in fact, so many RISC architectures, which were beautifully architected, incredibly well designed by some of the brightest computer scientists in the world, largely failed. And so I've given you two examples where one is elegant, the other one's barely aesthetic. And so yet x86 survived. And
install base is everything.
Install base defines an architecture. Not everything else is secondary. Okay. And so there were other architectures at the time. CUDA came out, OpenCL was here. There were, there's several other competing architectures. But the decision that we made that was good was we said, hey, look, ultimately it's about install base and what is the best way we could get a new computing architecture into the world. By that time frame, GeForce had become successful. We were already selling millions and millions of GeForce GPUs a year. And we said, we ought to put CUDA on GeForce and put it into every single PC, whether customers use it or not, and use it as a starting point of cultivating our install base. Meanwhile, we'll go and attract developers, and we went to universities and wrote books and taught classes and put CUDA everywhere. And eventually people would discover, and at the time, the PC was the primary computing vehicle. There was no cloud, and we could put a supercomputer in the hands of every researcher in school, every scientist, every engineer in school, every student in school, and eventually something amazing will happen. Well, the problem was CUDA increased our cost of that GPU, which is a consumer product, so tremendously, it completely consumed all of the company's gross profit dollars. And so at the time, the company was probably, worth, I don't know, at the time, $8 billion or something, $6-7 billion or something like that. After we launched CUDA, I recognized that it was going to add so much cost, but it was something we believed in. Our market cap went down to like $1.5 billion. And so we were down there for a while, we clawed our way back slowly. But we carried CUDA on GeForce. I always say that NVIDIA is the house that GeForce built because it was GeForce that took CUDA out to everybody. Researchers, scientists, they discovered CUDA on GeForce because they were all, many of them were gamers. Many of them built their own PCs anyways. In a university lab, many of them built clusters themselves, using PC components. And so that, that's kind of how we got going.
And then that became the platform, the foundation for the deep learning revolution.
That was also another great observation. Yeah.
That existential moment, do you remember, like, what were those meetings like? What were those discussions like, deciding as a company, risking everything?
Well, I had to make it clear to the board what we were trying to do, and the management team knew our gross margins were going to get crushed. So you could imagine a world where GeForce would carry the burden of CUDA, and none of the gamers would appreciate it, and none of the gamers would pay for it. They only pay a certain price, and it doesn't matter what your cost is. And so, we increased our cost by 50%, and that consumed, and we were a 35% gross margin company. And so it was quite a difficult decision to make. But you could imagine that someday this could go into workstations, and it would go into supercomputers, and in those segments, maybe we can capture more margin. So you could reason your way into being able to afford this, but it took a decade.
But that's more of like conversation with the board, convincing them. But you psychologically, because NVIDIA has continued to make bold bets that predict the future, and in part, especially now, define the future. So I'm almost looking for wisdom about how you were able to make those decisions, to make leaps like that as a company.
Well, first of all, I'm informed by a lot of curiosity. At some point, there's a reasoning system that convinces me so clearly this outcome will happen, that this will happen. And so I believe it in my mind. And when I believe it in my mind, you know how it is. You manifest a future, and that future is so convincing. There's no way it won't happen. There's a lot of suffering in between, but you've got to believe what you believe.
So you envision the future.
Yeah.
And you essentially, from a sort of engineering perspective, manifest it.
Yeah. And you reason about how to get there. You reason about why it must exist. We all reason it here. The management team will reason about it. All the people that we spend a lot of time reasoning about it. The thing that the next part of it is probably a skill thing, which is, oftentimes in leadership, the leadership stays quiet, or they learn about something and then they do some manifesto, and it's a brand new year. And somehow at the end of the year, next year, we're going to have a brand new plan. Big, huge layoff this way, big, huge organization change this way, new mission statement, brand new logos, that kind of stuff.
Yeah.
We've just I never do things that way. When I learn about something and it's starting to influence how I think, I'll make it very clear to everybody near me that, this is interesting. This is going to make a difference. This is going to impact that. And I reason about things step by step by step. Oftentimes, I've already made up my mind, but I'll take every possible opportunity, external information, new insights, new discoveries, new engineering, revelations, new milestones developed. I'll take those opportunities and I'll use it to shape everybody else's belief system. And I'm doing that literally every single day. I'm doing that with my board. I'm doing that with my management team. I'm doing that with my employees. I'm trying to shape their belief system such that when I come, the day I say, hey, let's buy Mellanox, it's completely obvious to everybody that we absolutely should. On the day that I said, hey guys, let's go all in on deep learning. And let me tell you why. I've already been laying down the bricks to different organizations inside the company. Every organization and everybody, many of the people might have heard everything. Most of the company hears, of course, pieces of it. And on the day that I announce it, everybody's kind of bought into many pieces of it. And in a lot of ways, I like to announce these things, and I imagine that the employees are kind of saying, Jensen, what took you so long? And in fact, I've been shaping their belief system for some time, and therefore leadership, sometimes it looks like you're leading from behind, but you've been shaping their, to the point where on the day that I declared it, 100% buy-in. But that's what you want. You want to bring everybody along. Otherwise we announce something about deep learning and everybody goes, what are you talking about? You announce something about, let's go all in on this thing. And your management team, your board, your employees, your customers, they're kind of like, where's this coming from? This is insane. And so GTC, in fact, if you go back in time, you look at the keynotes, I'm also shaping the belief system of my partners in the industry, and I'm using that to shape, the belief system of my own employees. And so by the time that I announce something, like for example, we just announced Grok. I've been talking about the stepping stones for 2.5 years. You guys just go back and go, oh my gosh, they've been talking about it for 2.5 years. And so I've been laying the foundation step by step by step. So when the time comes, you announce it, everybody's, what took you so long?
But it's not just inside the company. You're shaping the landscape, the broader global landscape of innovation. Like putting those ideas out there, you really are manifesting reality.
We don't build computers. We actually don't build clouds. We don't, as it turns out, we're a computing platform company. And so nobody can buy anything from us. That's the weird thing. We vertically design, vertically integrate to design and optimize, but then we open up the entire platform at every single layer to be integrated into other companies' products and services and clouds and supercomputers and OEM computers. And so the amazing thing is I can't do what I do without having convinced them first. And so most of GTC is about manifesting a future that by the time that my product is ready, they're going, what took you so long?
Yeah. So one of the things you've been a believer for a long time is scaling laws broadly defined. So are you still a believer in the scaling laws?
Yeah, we have more scaling laws now.
So I think you've outlined 4 of them with pre-training, post-training, test time, and agentic scaling. What do you think when you think about the future, deep future and the near-term future, what are the blockers that you're most concerned about that keep you up at night, that you have to overcome in order to keep scaling?
Well, we can go back and reflect on what people thought were blockers.
Mm-hmm.
So in the beginning, we were the pre-training scaling law. People thought, rightfully so, that the amount of data that we have, high quality data that we have, will limit the intelligence that we achieve. And that scaling law was an important, very important scaling law. The larger the model, the correspondingly more data results in a smarter AI. And so that was pre-training. And Ilya said, we're out of data or something like that. Pre-training is over or something like that. The industry panicked, that this is the end of AI. And of course, that's obviously not true. We're going to keep on scaling the amount of data that we have to train with. A lot of that data is probably going to be synthetic. And that also confused people, and what people don't realize is that they've kind of forgotten that most of the data that we are training, that we teach each other with, inform each other with, is synthetic. It's synthetic because it didn't come out of nature. You created it. I'm consuming it. I modify it, augment it. I regenerate it. Somebody else consumes it. And so we've now reached a level where AI is able to take ground truth, augment it, enhance it, synthetically generate an enormous amount of data. And that part of post-training continues to scale. And so the amount of data that we could use that is human-generated will be smaller and smaller and smaller. The amount of data that we use to train model is going to continue to scale to the point where we're no longer limited. Training is no longer limited by data, is now limited by compute. And the reason for that is most of the data is synthetic. Then the next phase is test time. And I still remember people telling me that inference, oh yeah, that's easy. Pre-training, that's hard. These are giant systems that people are talking about. Inference must be easy. And so inference chips are going to be little tiny chips, and they're not like NVIDIA's chips. Oh, those are going to be complicated and expensive, and we could make, and this is and in the future inference is going to be the biggest market, and it's going to be easy, and we're going to commoditize it, and everybody can build their own chips, and that was always illogical to me, because inference is thinking. And I think thinking is hard. Thinking is way harder than reading. Pre-training is just memorization and generalization, and looking for patterns and relationships. You're reading versus thinking, reasoning, solving problems, taking unexplored experiences, new experiences, and breaking it down into decomposing it into solvable pieces that we then go off either through first principle reasoning or through previous examples, prior experiences, or just exploration and search and trying different